Good afternoon. As Sue said, my name is Scott Gross. I'm with MCI, and in particular, May Engineering. I'm here to talk a bit about what we've done to extend our L2 VPN services through network convergence. This is going to be fairly high level, so not too many bits and bytes going by you here. We defined a goal to interconnect a number of our regional networks to extend our L2 VPN service across the U.S. and further to do so rapidly at minimal cost. The resulting network was to continue to support 802.1q, frame relay, and AL5 attachment circuits with inner working among all of them, and also to accommodate future deployment of broadcast or multi-point services such as VPLS. As a solution, we elected to build an MPLS network that would ride on top of the existing MCI IP infrastructure. And I'll continue to refer to these as the MPLS overlay and the IP core networks. The general components I'll refer to, which we're all pretty much familiar with, the customer edge, CE, which presented as an 802.1q frame or ATMA L5 capable router. The service edge, which is an MPLS LSR and also serves as the MPLS overlay edge. And the PE or provider edge, which is an IP router serving as the IP core edge. Here's a high-level diagram showing the L2 VPN service carried out to the CE. The service is supported by the MPLS overlay network, which is in turn then supported by the IP core network. So to accomplish this, we came up with three general requirements for the MPLS overlay network. The first requirement, and rather obvious, is a stable IP core. We certainly don't want to put this on top of an unstable IP core. Our IP network's been around for an extended period of time, so we have a very good idea of its stability and definitely had confidence that we could put this on top of it. We required that the IP core provide the MPLS overlay with regional diversity by maintaining multiple edge devices in a given region, which in turn can facilitate redundancy. So it wasn't enough just to attach a service edge to a provider edge with two links. We wanted to pull the provider edges apart and get some diversity there in case you have provider edge failure. Further, in the hierarchical structure of the IP core, it was necessary to have redundancy between the PEs and next level core devices, and that was already there. And of course, sufficient bandwidth is required throughout the core, such that all possible paths can handle the largest flows from the service edge. So as a rule, the links within the core had to be greater than or equal to the size of the PE to SC attachment circuits. And depending on the number of overlay networks that you were to build on top of that, you would, of course, have to accommodate the bandwidth on the back side. In this diagram, I'm showing two regions, R1 and R2. In each region, the SU node is provided with dual OC48 links. I should mention right now that we're doing OC12. OC48 is coming down the pike. Each connects to a different PE device to provide the diversity, as I said. The PEs are then linked into the remaining IP core following the same approach. Our second general requirement was to maintain service separation among the MPLS overlay and the IP core. By maintaining service separation, we were able to keep network-specific expertise intact. So organizations already familiar with the L2 VPN stuff and those with the IP core didn't have to go through a lengthy training process. So that enabled us to get the service to market quicker. The caveat is that this approach, is that the organization of fault isolation and detection can become more complex as you add overlay networks to the IP core. So coordinating maintenance windows and things like that can get tougher as this stuff gets layered on. So it's definitely important to stay ahead of that. We felt the best way to maintain the service separation was to achieve as much functional separation as possible. Therefore, our third requirement was to have separate IGP functionality among the MPLS overlay and the IP core. To meet this end, we employed GRE tunnels between the SC nodes over PPP links to the IP core using static routes for tunnel tail reachability. We chose GRE based on configuration simplicity, it's pretty straightforward, and vendor availability. Our vendor was able to turn around GRE implementation very quickly, so we could get it out there. So GRE met our requirements, and it also allows the IP core to continue to add other services without changes being required on our MPLS overlay network. But there are a couple noteworthy items. Additional services may require changes to the IP core. So you add a service over here, well, they may need to so it may directly affect the IP core, the operation of the and the operation of the MPLS overlay network. So this may be in the form of a maintenance outage or possibly degradation of the MPLS overlay due to increased utilization in the IP core. Secondly, the overlay IGP, in our case integrated ISIS, is at the mercy of the IP core IGP and its ability to calculate the most efficient paths through the IP core network. While the overlay IGP hop count is not affected by the IP core, the latency between hops is, and therefore can affect the overlay IGP routing decisions. Here we have the various elements that are serviced by the GRE tunnels. In the tunnel, we have ISIS running, RSVP for LSP tunnel label distribution, and LDP for VC label distribution. In the MPLS over GRE sense, we have our functioning tunnel LSPs carrying draft Martini circuits composed of Ethernet frame and ATM. Here's the anatomy of the GRE header per RFC 2784. This header can vary in length depending on the options chosen. In our case, the checksum present bit is set to 0, indicating that the optional checksum and reserved 1 fields are not present. This results in a 4-byte header. This is based on the recommendation from the IETF MPLS in IP or GRE draft. I've also listed the 3 protocol type values that are employed in our implementation for anyone who's terribly curious. Once the GRE header is encapsulated in IP and sent over the IP core, it runs the risk of fragmentation. If fragmentation occurs, it is the tunnel tail's requirement then to reassemble the packet. And that sucks up resources that should otherwise be used to forward packets more efficiently and quickly. So we want to avoid fragmentation. PMTU could be implemented to meet this end. However, in our case, that functionality was not available. But we had 2 tools, again per MPLS in IP or GRE, setting the don't fragment bit in the IP header. And secondly, configure the MTU setting in the IP core to accommodate the largest possible packets from our service edge. We're able to support up to an 8206 byte MTU on our 8021Q attachment circuits. So using that as an example, we add the MPLS, GRE, and IP headers to come up with a combined 32 bytes of overhead. And that results in an IP packet totaling 8,238 bytes. So from that, we have our MTU requirement for the IP core network. The result that we set is that we set the IP core IP MTU to 9100, which clearly accommodates the 8,238 bytes, and media MTU of 9192, which allows L2 header growth up to 92 bytes, which is a whole lot. So some of the design details, I already talked a bit about the diversity and redundancy at the SE to PE attachment circuits. We also stretched this out from SE to SE with our GRE and LSP design. In this diagram, we have 3 SE nodes, SEs A, B, and C. Using the 2 OC12 connections labeled Link 1 and Link 2, GRE tunnels are built between the SE nodes in support of multiple LSPs. A total of 4 GRE tunnels are configured. On Link 1, tunnel A to B1, tunnel A to C1, and on Link 2, tunnels A to B2 and A to C2. Each of these tunnels then support 2 LSPs. A primary is depicted in green, and a backup is shown in brown here. So for instance, Link 1 has a primary LSP to each node and supports the backup LSPs for Link 2. And as indicated in that slide, dual GRE tunnels are built to each corresponding SE node to form a full mesh. Here's a view of the fully meshed tunnel construct, and this is indeed actually what we have out there today. We have 3 service edge nodes tying into the IP core. We do have more POPs out there, but those are tied in direct links to the SE devices that are shown here. So again, a full mesh. We used /30s, the point-to-point links, so that's obvious. We used RFC 1918 addresses for our tunnel interfaces. No need to waste good address space on stuff that's not routed. These fully meshed tunnels then support a full mesh of tunnel LSPs. So here's a logical view of the fully meshed LSP construct. Again, primary and backup per tunnel. And again, 2 tunnels between each service edge. So we got quite a bit of diversity and redundancy built in there. And so in summary, our L2 VPN service was successfully extended coast to coast with RTDs averaging 77 milliseconds. That's up to 4470. We were able to deploy in less than a year, and we did it at minimal cost. The networks were already there. We just had to purchase some interfaces for the IP core and then bring up the links. And in most cases, our service edge devices are in the same POP as our provider edge devices. So it's just a fiber run. Thus far, as you saw, 3 nodes, right? So far we haven't experienced a significant increase in operations complexity or scalability. And scalability down the road is certainly a concern. But there's a lot more growth ahead of us, and indeed there's going to be a lot more options as new technologies emerge, so hopefully we can meet those ends. So we'll see what the future brings. And there are some references that are interesting reading. And so if anyone has any questions.